Today's lesson is about continuous functions. There are 5 graphs on the screen as you see, and all of them are discontinuous, of course. So let's see why we call them discontinuous. Look at the first graph. So what is the left limit at 2? The left limit at 2 is 1, and the right limit at 2 is 3. Since left and right limit are not equal, function has no limit at 2, or limit does not exist. So since limit does not exist at 2, function is discontinuous. So limit dne, therefore f is not continuous. Look at the second graph. In the second graph, limit at 2 does exist. But the y value at 2 is undefined. So f of 2 is undefined. We can actually say that the domain of this function is all real numbers except 2. So it means another reason for discontinuity is that the y value at the point is undefined. Now look at graph number 3. Again, limit at 1 does exist, and it's equal to 2. The y value at 1 also exists, as you see. F of 1 equals -1. So even though limit does exist and y value also is defined, but since they are not equal, function is discontinuous. So in graphs 2 and 3, as if you removed one point of your graph. Look at the graph number 4. So at 1, we have a vertical asymptote, and obviously when we have a vertical asymptote, function cannot be connected, and it's discontinuous. So it means one of the other reasons for being discontinuous is the existence of the vertical asymptote. So graph number 5 is nothing new. It could be like categorized as example 1. Just for like having more examples, we can look through this one as well. So left limit at 0 is 1, and right limit at 0 is -1, and f of 0 is also 1, but actually we don't care about f of 0 in this case because limit already does not exist and function is discontinuous. So if we summarize all these cases that function is discontinuous, we can conclude that when limit does not exist, function is discontinuous. But in some cases, like 2 and 3, function has limit at a point, but the problem is the y value at the point. So it means if limit does exist, the y value must equal to limit in order to have a continuous function. Therefore, I'm going to write the definition of continuous functions at a point. So f is continuous at x equals a if limit at a does exist and is equal to f of a. Mathematically saying, limit of f of x as x approaches a negative equals f of x as x approaches a from right side and equals to f of a. So we can combine these two and write a new definition, same, but more brief, because this one stands for existence of the limit. So it gives us an instruction, clear instruction, that if you want to check whether or not a function is continuous, you need to calculate left limit, right limit, and f of the point or y value at the point to see if they are all the same, then function is continuous. Let's have an example. F of x equals x squared for x less than 1. At x equals 1, it's 1, and when x is larger than 1 is x cubed. I want to see if this function is continuous or not. So the only point that we need to be concerned about is 1, because before 1 we have a quadratic function. X squared is a polynomial and is continuous everywhere. For x larger than 1 also we have a polynomial which is continuous everywhere. So it means the only point that we need to double check is the splitting point, which is 1. So what is the right limit at 1? We use the bottom function, because 1 positive or right limit means x is a little bit larger than 1. So which function stands for x larger than 1? This is the bottom one. So you plug in x 1, so you'll get x cubed, right? 1 to the power 3, which is 1. So f of 1 negative or left limit is 1 squared, which is 1. And f at 1 is defined to be 1. Oh, all of them are the same. So it means function is continuous at 1. So the next example, x squared when x is less than negative 1, when x is between negative 1 and 1, and when x is larger than 1, so it's x cubed 2x minus 3. So the points that we need to check whether function is continuous at are negative 1 and 1, the splitting point obviously. So let's calculate the left limit at negative 1, which is 1. The right limit at negative 1, which is negative 1 cubed, which is negative 1. So it means at negative 1, limit does not exist. And we know that when limit does not exist, function cannot be continuous. So we have one discontinuity at negative 1. So let's go over 1. So right limit at 1 is negative 1, and left limit at 1 is 1. Again, limit does not exist. So it means this function has 2 discontinuity. Next example, f of x equals x minus 1 over x squared minus 4. So here the only problematic points are the points that make the denominator 0, because when denominator is 0, function is undefined. So when your function is undefined at a point, how could it be continuous? So we set the denominator 0. So x becomes positive and negative 2. So we have 2 discontinuity here, which are 2 and negative 2. And the last example of today today's lesson is this one. So we are given that this function is continuous everywhere for all real numbers. So we are going to find A and B. Since we know that function is continuous everywhere, so it means f must be continuous at -1 and 0, because these 2 points are the only points that matter. So let's see. So we know that function is continuous at -1, so it means left and right limit must be the same. What is the right limit at -1? So -1 cubed, which is -1. What is the left limit at -1? So it's -a plus 1. From here, a becomes 2. Also, since we know that this function is continuous for all real numbers, so it should be continuous at 0 as well. So f of 0 positive and negative must be the same. F of 0 positive should be b, and f of 0 negative is 0, so b is 0. So this brief lesson was about the definition of continuity. In the next lesson, we will go over removable discontinuity and some complications, some like more challenging questions. See you in the next lesson.